to product, reaction mechanism is asking the question, what is happening in that organic reaction? What is happening in that transformation? So, last lecture, we talked about thermodynamics and kinetics. They are inherently related to reaction mechanism, but we will not talk about too much detail in that regard. So these, just as a quick reminder, these are the topics we discussed in our last lecture. Again, whenever we're saying thermodynamics, we're saying, hey, we're having a reactant, we're having a product on two sides of the reaction. Which one of them is more stable? And then here we have the kinetic, which relates to the rate of the reaction or how the reaction is taking place in that transition state. So reaction mechanism is inherently related to that transition or the rate of the reaction. But for now, for this class, we won't go into too much detail. But you'll probably see that again when you talk about specific reactions, especially in Chem 14D. All right. So getting started for today. Today, we'll first talk about the general rules of reaction mechanism, and then we'll see several different examples in how to do arrow pushing, how to draw the reaction mechanism, and how to use the reaction mechanism to actually derive what is happening in your reaction mixture. So there are like millions of chemical reactions available. You can imagine you have so many different chemicals that are interconverting to each other. But at the very heart of all organic chemistry, we have probably hundreds of possible reaction mechanisms that are operative. So a lot of reaction can take place via similar reaction mechanism. Or in this case, when we say reaction mechanism, you can also give it a more settled definitions. They are just generalized reaction pathways that's connecting your reactant and products. So that's the first question. What is reaction mechanism? Second question is, why do we care about reaction mechanism? I mean, why do we need to know how things are taking place? So here's the thing. You can have multiple reactions that takes place via the same reaction mechanism. So that's actually a good news to us because we don't need to remember everything. So I'll use the electrophilic aromatic substitution as an example. So this is one of the equation or one of the reaction you'll see in 14D. I'm not going to test you on this, but I found this to be a very nice example in showing how reaction mechanism is connecting so many different transformations. The reaction itself is simple. You start from an aromatic group, and then here you have an electrophile. So electrophile is a topic we discussed before. Electrophile basically means, hey, this is a species that's electron deficient. It has a partial positive charge there. It can be attacked by some electron-rich group. So in this reaction, the attack of the benzene onto the electrophile will form your carbocation intermediate. And then this carbocation intermediate recombine with that X minus to form the product. So here, depending on what your electrophile or what your E is and what your X is, you can have all kinds of reaction. So I'm just showing here some examples here. So if your X, if your electrophile is halogen group, people call it halogenation. If your electrophile is NO2, people call it nitration. And if your electrophile is an alkyl group, when I say alkyl, it basically means methyl, CH3, ethyl, CH2, CH3, etc., etc. So that's called the Friedel-Crafts alkylation. So we have so many different reactions in organic chemistry, but halogenation, nitration, Friedel-Crafts alkylation, they all have the same reaction mechanism, which means you don't have to remember everything. You just need to know how things are taking place, and from there we can easily derive or predict what's the product of a chemical transformation. So that's our second question. Why do we care about reaction mechanism? And the short answer here is it's doing you a favor. It's by understand the reaction mechanism, you're saving lots of time of yourself. You don't need to remember, you don't need to memorize all possible chemical reactions. Use the mechanism to connect all of the transformations of the same class. So that's the two general questions. And now we're moving on to our major topic of today. So how do we actually draw reaction mechanism? And here we'll use 5 different types of transformation, and we'll go over them one by one. But in general, what we're doing is called arrow pushing. So I'm just going to highlight it here. So when we say arrow pushing mechanism, what exactly we mean is we use this curved arrow, which is this little purple arrow here, to show or to indicate how do we expect the electron flow from a more electron-rich part of the molecule to a more electron-deficient part of the molecule. And in that process, by imagining how electrons are moving in between the molecule, you can imagine new bonds being forming or old bonds being breaking. All right, so the way we draw it is a curved arrow. Again, it's showing the flow of the electron. So we always start from electron-rich groups, either it's a double bond or a lone pair, and moving to a more electron-deficient point. We'll see the application of this in examples here. So if you have a blank note printed out with you, good, we can work on it together. If you like to write down the equation, you can also write it with me. But if you don't feel you can write fast enough, just pay attention to what I am doing and get more practice later on. Like, don't worry about writing everything down, because I will be posting everything I have in the annotated notes. All right. First example here, dissociation of covalent bond. So this actually have 2 parts. The first part is the dissociation of a polar covalent bond. So first reaction, dissociation. So we start from a polar covalent bond. And here, let's just assume our atom A is more electron positive, maybe a carbon, and our atom B is more electron negative, maybe an oxygen. So let's just say this one is more electron positive, and this one is more electron negative. So what we're doing here, it is a dissociation. So now the electron is in my chemical bond here, right? So when we're drawing the reaction mechanism, you want to ask yourself the question, where are my electrons? Where is electron density? So the answer here is the electron now is in your polar covalent bond. You don't have to draw that dot, but here I'm just quick indication in where your electron pair is. When you're drawing that arrow pushing, you start from the electron pair that goes to somewhere you like it to be. So in this case, we're talking about a dissociation. We're forming a cation on the more electron positive atom A and an anion in the more electron negative atom B. So in this case, what we have is electrons starting from the single polar covalent bond, and the electron ends up on my atom B. Right, so if you imagine how that electron flow, where we have is electron moving from the chemical bond to my electron negative atom B. So by doing the arrow pushing here, what we're saying is electron is flowing from the single polar covalent bond to the electron negative atom B here. And the result of this reaction is forming of a cation on the more electron positive atom and an anion on the more electron negative atom. All right, so here that's what we did, and this is just a quick statement in what I'm doing when I'm drawing that arrow. Again, what we're doing is electron is moving from that covalent bond into my electron negative atom to form that anion. Let's see another example in real world. So this one is a hypothetical example with hypothetical atom. So let's do one example together. So here on the left-hand side, again, this one, I'm just drawing the bond line formula. If it's more helpful, you might want to draw the Coquille formula, which is write out all the CH bond. So that's the Coquille formula, or you can also write out the condensed formula. So this is a quick review on what these formula mean. CH3, CH2, carbon binded to 2CH3 and bromine. So that part is a quick review. So now our question is, how do we draw our arrow pushing to indicate the electron flow in this transformation? And you look at this reaction first, and you identify, hey, here we're breaking the carbon bond and the bromine bond. So the electron is flowing from this covalent bond into bromine to form that bromine anion. And the result of this dissociation of the polar covalent bond is form a carbocation or a carbon-centered cation. And here, forming of the bromide anion. All right, so the way we draw it, again, we're using this arrow to show where your electron is moving. So this is the example of dissociation of a polar covalent bond. Try not to remember it. Try to just think about it. What is happening? We're just using the arrow to show where the electron is moving. You look at the reactant. You look at the product. You think about where the electron is. And then you draw the arrow accordingly. So that's our first example, dissociation of a polar covalent bond. Next example here. What about a nonpolar covalent bond? So it's a little bit to my surprise that this part is not covered in your textbook, so you might want to pay a little bit more attention to what I'm going to say because it's not in your textbook. So when we have polar covalent bonds, what we're forming is a pair of cation and anion, where the electron density ends up on your anionic species or the more electron negative species. But what if we have a nonpolar covalent bond? And the dissociation of your nonpolar covalent bonds, which in this case we're using the bromine Br2 as an example, dissociation of Br2 would form two radical species with that electron on each of the atom. So the way we do it is instead of having the normal arrow, which means we're moving the electron pair, we're moving two electrons at the same time. Now what we're doing is with this single-sided arrow to indicate the movement of just one single electron. All right, we're just moving one single electron to each of the bromine atom to form two free radical species. Or in the other word, what we have is one electron in the nonpolar Br-Br bond moves to one bromine atom. So we have two of them in that covalent bond. Each electron moves to each bromine atom, forming two free radical species. So these are free radicals. Questions? So the question is, what is a free radical? Free radical is just species with single unpaired electron. So in this case, if I write out all the electron of that bromine, what we have is this one is a singly non-paired electron. So let's look at some more examples in drawing out the single-sided arrow to form the free radical species. For example, in this case, we're imagining this quite extraordinary molecule. It is called a bicyclobutene. And the carbon-carbon bonds we're highlighting here, this one is almost a nonpolar covalent bond. It's a covalent bond between two carbon atoms, so naturally they're nearly nonpolar. What we're saying is now dissociation of this nonpolar bond, or homolysis of this nonpolar covalent bond, can form two carbon-centered radical species. So how do we do the arrow pushing to indicate this process? So likewise, we have two electrons in that single bond, and then one of them goes to this top carbon, the other goes to that bottom carbon. And what we end up is two carbon-centered radical species. All right, and again, when we say free radicals, what we mean are these atoms with singly unpaired electrons on them. Let's do one more example together, which is a peroxide. Again, this is a very symmetric molecule. That oxygen-oxygen bond is a nonpolar covalent bond. And now, for example, I can change the way I ask question about arrow pushing. It's now I give you the arrow, and I tell you the homolysis of this bond would follow this reaction mechanism, would follow this arrow pushing reaction mechanism. Can you predict what is the product coming from that transformation? So again, what you're doing is thinking about what is happening. So the electron in the oxygen-oxygen single bond, those two electrons will break that non-polar covalent bond. Each electron goes into one oxygen atom. So the product here is two oxygen-centered radical species. Yes? We don't have a negative charge here because we're just symmetrically cleaving that bond. We don't have a negative charge. It's a free radical. It's a different type of active species. So that's actually a very good question, is what about charge? So if you look at our previous scenario, what we have here is, again, in this reaction, our charge is still balanced up. It's a plus charge on the carbocation. It's a minus charge on your bromide, right? So the charge on both sides of your reaction still needs to balance up. But when we're talking about homolysis or the cleaving of that polar covalent bond to form the radical species, it is a free radical, yes. It has unpaired electron, yes, but it does not have a charge. All right, so that's our first class of reaction, which is dissociation. Either dissociation of a polar covalent bond to form a cation-anion pair, or dissociation of a nonpolar covalent bond to form free radicals. I'll pause here to see if we have any questions. This is the style we'll be going. We have 4 more classes of reaction mechanisms we're going to look at together. Yes? Right. So when I say there are different ways I can ask the question, it's, for example, I can give you the starting reactant and I can give you the product. I ask you to draw the arrow pushing to show me like now what is the mechanism connecting these two species, and then you draw the arrow pushing accordingly. The other way I can ask the question is, for example, now I give you the reactant. I give you the arrow pushing mechanism. Can you predict what is the product? So in this case, you look at it, you read the arrow and derive where the electron is flowing and what is your product, which is my oxygen-centered radical. But we need 2 of them just to balance it up. All right? Yes? So the question is, how do we know what happens when a covalent bond breaks? The quick answer here is, I'll tell you, first of all, it's a dissociation of a covalent bond. And then it depends whether your covalent bond is a polar covalent bond or a nonpolar covalent bond. So a polar covalent bond would dissociate into this cation-anion pair because there's an obvious difference in electron negativity. But if we're talking about breaking a nonpolar covalent bond, then we have the radical species. Because they're nonpolar, the electron negativity is almost the same, so the electron doesn't have a preference in where they're going. So each electron going to one direction. All right, so that's a dissociation. Let's move on to look at the second cause, which is obviously now we know how to break chemical bonds. We can form new chemical bonds. So here, when we're forming new covalent bonds, what you can imagine is electron pair on one of the atoms. Again, we're using the generalized form A and B. You can imagine an electron pair on your species B is moving towards another atom A. So in the process of electron moving in that direction, or in this case, the electron comes solely from B to A. So this electron pair comes from anion B, attacking your cation A in forming a new covalent bond. Or this is more or less the reverse process of the dissociation reaction we talked about. All right, so when we're drawing the arrow, you look at your reactant, you think about where your electrons are, and then you draw the arrow accordingly. So, some examples of this formation of the covalent bonds. Let's look at some acid-base reaction, which we'll see in more detail on our next lecture. But let's just have a head start in looking at the electron movement in acid-base chemistry. So example 2-1, that's a Bronsted acid-base. We'll go over that on Friday. But here, if we look at the reactant, we have the hydroxide anion. We have a proton. So apparently my electron is in my OH minus. And the new chemical bond that's forming is between the hydrogen and the OH. So how do we draw the arrow pushing? We start from the electron, and that's pointing towards that proton. It's pointing towards that electron deficient species. And we're forming the new chemical bond, which is shown here. All right, so again, the most important thing when drawing your your arrow pushing is just keep in mind, you always start from the electrons. You always start by thinking about where my electrons are, and then you draw the arrow accordingly. So that's a Bronsted acid base. Let's see one more example, which is the Lewis acid base. So this one, again, we'll talk about more about Lewis acid base on Friday. But here's the idea. We start from the lone pair on the nitrogen. So that's where your electron is. That's where your electron pair is. And here, if we look at aluminum and the halogen, one of the things you can quickly derive is your aluminum center is going to be more electron negative, or you have a partial positive charge on the aluminum. So it just boils down to simple Coulomb's law. If you think about it, your electron is somewhat negative, and they want to move to the more electron-positive part and form a chemical bond. So what we have here is this arrow. We're pushing the electron from the lone pair of nitrogen to the electron-deficient part of my aluminum chloride. And what we're forming here, this one I want to pause a little bit and just ask you to do a quick practice. Can you assign the formal charge of aluminum and nitrogen in this species? Let's quickly do it. Aluminum naturally has 3 electrons around it. Now it has 4 chemical bonds. If you use the equation we have, we'll see the aluminum has a negative charge on it. Nitrogen, on the other hand, normally has 5 valence electrons. Now it's forming 4 chemical bonds. So this has a positive charge here. All right, so that's just a quick example in how easily we can merge Lewis dot diagram to arrow pushing mechanism. You can easily imagine what I give you is just like this part. And then I say, like, hey, now we know this reaction is taking place. This is the arrow pushing. Draw the product and also write out the formal charge in that product. So that's just a quick reminder, and we may be able to connect different concepts of in your homework or assignments. And what we have here, this one is actually called a Z-iron. Means you have the charge separated species in your product there. Just as a very quick demonstration. This is what I said, like I'm not going to test you on nomenclature, but I'll just keep talking about the name of these active species, the name of these chemicals, so you're familiar with it. All right, that's our second example, which is the forming of a new polar covalent bond. The reaction of the free radical species is a little bit more challenging, so we'll leave that for now. I'm not going to talk about the formation of new covalent bonds from free radical species. I'll save it for later. All right, now we know how to break a chemical bond. We know how to form a chemical bond. What about we have forming and breaking of chemical bonds all happen at the same time? So that is called a substitution reaction. So it's a simultaneous making and breaking of 2 chemical bonds. We're forming one bond and we're breaking the other. Again, if you think about it, we look at this is a generalized reaction, and you just look at it and think about what is taking place. This is where my electron is starting from. It's on my atom X. And then this is the starting molecule, which is my AB. What we end up with is a new chemical bond between X and A, and a breaking of the AB bond. So how the electron is moving. If you look at it, it's going to be we're forming the XA chemical bond first. Well, at the same time, we're also breaking our AB chemical bonds. So the way electron is moving is simultaneously when your X electrons on X minus on your anionic starting material, forming a new covalent bond with atom A. And at the same time, we're breaking the covalent bond between atom A and atom B. So typically, the substitution reaction requires my AB to be a polar covalent bond. We'll have a partial positive charge on my atom A and a partial negative charge on my atom B. So that's the generalized picture of a substitution reaction. And let's look at some more real-life examples together. Let's do 3-1 first. So we start from a OH minus. Apparently that's where your electron is at the moment. And we look at our reactant here. This is my methyl chloride. And as it's a methyl chloride, our carbon is more electron positive, where my chloride is more electron negative. So now we look at how the reaction is forming. We're forming a new oxygen-carbon bond, and we're dissociating our carbon chloride bond. So when we're doing the arrow pushing, we're forming the new oxygen-carbon bond, and then we're dissociating our carbon-chlorine bond. So the electron in the OH minus forms a covalent bond with carbon, and at the same time, the carbon-chlorine bond will dissociate to form the chlorine anion. Ooh, sorry. So in this process, in organic chemistry, we can also use terminology like nucleophilic. So when we say nucleophilic, we're basically say, hey, this is a reactive species that is rich in electron, has lots of electrons around it. And in here, when we have this carbon center, we can say it to be electrophilic. Or it is relatively electron deficient because it's binding to chlorine, an electron negative atom. So those are the terminology we use a lot in organic chemistry. There are new terminology. There is nothing fancy. Nucleophilic just saying, hey, we have lots of electron density here. Electrophilic just say, I want electron. It's a species that wants electron. All right? Yes?
So the example that you drew, it looks like is there a proton from the environment that takes place for the chlorine?
So the question is there going to be a proton in the environment that's balancing up with the chlorine minus? I'm not sure I follow your question here. So if you look at the number of atoms and number of charge on both sides of the equation, they are balanced up. We start from a negative charge here. We end up with a negative charge on the chlorine. We can talk more after class. All right, let's do one more example together. So likewise, this one is more like a Bronsted acid-base reaction. You have a OH minus. You're reacting that with hydrochloric acid. And in this process, we're forming the new OH bond. And at the same time, we're dissociating that HCl bond. So what we have is we're pushing it this way. And likewise, in the HCl, we know this one is a partial positive charge. This one's partial negative because chlorine is more electron negative. Yes?
So in this case, the plus sign represents there are two reactants.
So I don't like to think about this process as two reactions. It's a one substitution reaction where you're simultaneously making a bond and then forming a new bond, breaking a old bond. So it's a simultaneous process. It happened all at once. Right, we have two reactants coming together, yes. But the reaction itself is still a simultaneous reaction. All right, so let's move on. Now we know the general reaction of our single bond. You can break a single bond, you can form a single bond, or you can also simultaneously breaking and forming one single bond, breaking a new old single bond and forming a old single bond and forming a new single bond. But these are all reactions of single bonds. And now we can move on to look at reactions of pi bonds or double bonds. So for reaction of the double bonds, we have two different types of reaction we want to look at. They are both addition of double bonds. But the funny part about our double bond is it can act both as a nucleophile and also as an electrophile. So what does that mean? So if we think about our double bond here, you can have a polar double bond. For example, again, let's just imagine our A to be more electron positive and B to be more electron negative. So the addition of a nucleophile X minus onto my AB, the double bond species, is more like what we did in our substitution reaction. So the electron is flowing from X to A at the same time from the double bond to B. So this process, we're forming a new XA single bond, and this double bond basically gets reduced back to a single bond. And since B is our more electron negative atom, we have our new anionic charge on our atom B. Yes?
X will be more electronegative than B. X cannot be.
So in this case, no. Because we're forming the new XA bond, the charge needs to be on your atom B. So when we say the electron negative, we're comparing the relative electronegativity between A and B. We're leaving X as itself. After forming that covalent bond, your X will no longer have any charge. Yes?
How did you determine that B was more electronegative?
This one is a pure hypothetical scenario. We'll see the actual application of the nucleophilic addition. So let's just see some real chemistry reactions here. Again, we start from our OH minus. That's so far my favorite nucleophile. And here, what we're reacting with is a formaldehyde. So if you think about a formaldehyde, we're talking about a carbon-oxygen double bond. So here, my carbon is obviously less electron negative comparing to oxygen, right? Oxygen is much closer to fluorine. It's a very electron negative atom. So what we end up is forming this intermediate, or this species here. So let's just draw the arrow pushing together. So we start from the OH minus, attacking the more electrophile carbonyl carbon, and the electron in that double bond move into the oxygen. So what we have here, we have this new CO bond. So that's the new sigma bond formed. And here, the CO bond used to be a double bond. Now it's being reduced to a single bond. And our charge is now on the oxygen. All right, so lots of things is happening, but no need to remember all of it. You just look at our arrow pushing and just think about how the electron is moving in this chemical reaction. Let's do one more example. This one, I'm just going to leave it here, so you can work on it a little bit before I show you the answer. And again, we can look at what they are. So here, between the nitrogen and the carbonyl carbon, so this CO double bond is a carbonyl functional group. So this is the new bond that's formed. And then the CO double bond is being reduced. And then we have a new lone pair on the oxygen. All right, so naturally, if you look back to our arrow pushing, again, we start from the lone pair attacking the more electrophilic carbonyl carbon, and the double bond goes to the oxygen. And in this case, the carbon is more electron positive, the oxygen is more electron negative. So to answer some of your question, in my generalized A-B reaction, I'm just saying one of them is more electron negative. In the actual reaction, it will be very obvious. It's like going to be a carbon-oxygen bond or a silicon-oxygen bond. So something that's obviously electron negativity different. All right. So this is the first reaction of a double bond. So in this process, if we go back to our general reaction, what we have is our X minus, whether it's minus or just a lone pair, it doesn't matter as long as it has a lone pair. It can also be a neutral species. So this lone pair electron attacks our more electrophile atom in the molecule. So when we say electrophile, it probably connects to an electronegative atom, making this double bond a polar bond. And at the same time, this double bond is being reduced to a single bond. So again, it's a complicated process. We're forming a new bond, we're breaking a double bond, we're reducing a double bond to a single bond, and we have new lone pair that's transferred into the electronegative atom. So this is called the electrophilic addition to a polar double bond. The last example we're going to do together is called electrophilic addition to double bonds. So now it came to the special part about a double bond. So we have pi electrons in your double bond. So AB is a generalized form. So the electrons or pi electrons in your double bond can also act as nucleophile. So when we say the double bond on my the pi electron in my double bond can act as nucleophile, naturally it can react with electrophiles. Electrophile or electron deficient species. And what we end up with is now the arrow comes from the electrons, comes from your pi electrons, comes from your double bonds. So it flows to your electrophile. The result is the same. We're forming a new bond between A and, well, we're reducing that double bond between A and B, and we're forming a new bond with that electrophile. For some reason, I have Y there, but it should be electrophile. Which one of them is forming that bond with electrophile depends on the nature of that of the species we're talking about. So the example here, let's look at it. Let's look at a real example. So what we have is starting from a double bond, has the internal position and the terminal position. So this double bond is going to attack a proton like H+. And the result here is we're forming a carbocation intermediate. So if we want to figure out where that hydrogen is going to end up, it relates to the stability of this product that's being formed. It's a little bit beyond this class. For this class, I only expect you to know how to draw the arrow pushing. So both of them is correct. But we'll talk about reactive intermediate, and you'll see why this one is selectively formed over the other. You could also have examples where we're merging these two concepts, and I can ask you to draw the resonance structure of your product by doing additional arrow pushing. So in my example 4-4, what we have is we have the double bond acting as electrophile, attacking the proton to form a new chemical bond. So it's either here, or if you look at our product here, this can undergo additional arrow pushing. And this is actually a resonance structure. And this hydrogen remains the same. So these two species are called allylic cation. And they are stabilized. Resonance. All right, so occasionally people also use arrow pushing to show how electron is moving when we're drawing different resonance structures. So arrow pushing is just a tool. It's just tell you where your electron is moving and how it is moving. And you need to know how to draw the arrow pushing. It's always coming from the electron pointing towards the destination of that electron pair. We have 5 more minutes, so let's do some more comprehensive problems together. I left 2 comprehensive problems in the annotated note. We might not have enough time to finish all of them, but you can also work on it yourself. So this first example is reads, now imagine we have a very important organic reaction called tautomerization. So I give you the generalized reaction mechanism, and can you draw a valid proposed mechanism? So this is what I give you. We start here, and I also tell you where my first step what my first step looks like. All right, so what we have in our first step, this one is almost like a substitution reaction. But instead, the first step is this one is making a new bond between the hydrogen and the base. And the electrons in this double bond, in this CH bond, is transferring into that carbon there. So what we end up with is a structure like this. So now in this anionic species, what we can do is to draw, just to think about how your electron can move. This one is very nucleophile. It's a carbon-centered carbonyl species or carbon-centered anion species. And this carbonyl group, this one is a polar double bond. Right, so this one we have the partial positive charge and the partial negative charge. So when we're doing it, you can easily imagine this lone pair attacking the partial positive charge of the carbonyl carbon and goes to react with the, and the electron in the double bond is moving towards the oxygen. So this one is like a nucleophilic addition to your double bond. But in this case, what we're actually having is the resonance structure of this carbonyl. All right, and now we still have the H base hanging around. So in this H base, you'll have the anion attacking the hydrogen and goes back to the base. And we end up with our product. So in organic chemistry, the left-hand side, we call it the ketone form. So that's a general keton. On the right-hand side, that's our enol. You'll see that in 14D again. It's a tautomerization between keton and enol. All right. So today we covered a lot of examples. We'll do more of these examples in your discussion session next week. So arrow pushing is very important in organic chemistry, especially if you don't want to remember all millions of reactions. So I'll pause it for now. If you have any questions, I'll be here.